To fabricate electronic devices like diodes and transistors, semiconductors are used widely nowadays. Silicon, germanium, gallium arsenide, these are some of the popular semiconductors in electronics industry nowadays. Semiconductors are materials whose conductivity is low when compared to the conductivity of conductors or metals. Why the conductivity of semiconductors is low? To understand this point, consider silicon or germanium. These are tetravalent materials. It means in the outer orbits of atoms of these materials, there exists 4 electrons. All these 4 electrons, they remain fixed. They remain bonded in covalent bonds. Hence, they are not free. So, free electrons are not available in silicon or germanium, and this situation is at 0 degree Kelvin. If we consider temperature above 0 degree Kelvin, then there exists a possibility for these covalent bond electrons to take energy from the surroundings and become free. When they become free, a hole is also created for each free electron, thereby generating a free electron hole pair. Then current carriers, charge carriers, mobile carriers come into being, giving rise to certain amount of conductivity. Therefore, at 0 degree Kelvin, the conductivity is 0 for semiconductors. It is non-zero only at temperatures above 0 degree Kelvin. This conductivity too, it is small. When a semiconductor is pure without any foreign atoms, that semiconductor is called intrinsic semiconductor. Intrinsic semiconductor should not contain any foreign materials. Then only it is intrinsic. Electronic devices Semiconductors Part 1, Series on Semiconductor Devices and Circuits, Lecture number 1.11, PN junction diodes and transistors. These are the only electronic devices. When I say PN junction diodes, I mean the family of diodes. In this family, there exist several varieties of diodes. Ordinary diodes that are used for rectification, clipping, clamping, etc. This family also includes special diodes like light emitting diodes, photodiodes, varactor diodes, tunnel diodes, and several other varieties of diodes too. So PN junction diodes, they are huge in terms of variety. Of course, all of them, they have certain common properties like all are two-terminal devices, all are unilateral devices, all are nonlinear devices, all are with a PN junction. Similarly, when I say transistors, I don't mean a single type or a single component. I mean a family, a group in which several types exist. In transistors, there exist bipolar junction transistors. In this family, there exist field effect transistors. Again, in field effect transistors, there exist junction FETs and MOSFETs, and several other varieties of transistors are also there. So here diode refers to a family name. Here transistor refers to a family name. In each family, several varieties, several types of diodes or transistors exist. Both these families of devices, they are made with semiconductors. In fact, semiconductor is the basic material that goes into the design of diodes and transistors. In the present session, our focus is on semiconductors, their properties. We try to understand the nature of semiconductors with the help of energy band diagrams in the present session. Now let us move further to begin the session. Electronic devices. These are two in number, junction diodes and transistors. Notice diodes can also be constructed with vacuum tubes. Transistors are also can be fabricated with vacuum tubes. In such case, they are called triodes. Junction diodes refer to diodes that are fabricated with semiconductors. Transistors refer to triodes that are fabricated with semiconductors. So we are basically in semiconductor electronic devices. And these are two. One is diode, another is a transistor. A few points regarding diodes. Diodes are two-terminal devices. These are nonlinear devices. These are unilateral devices. Out of the two terminals, one terminal is called anode, other one is called cathode. These are nonlinear and also unilateral devices. Their properties are direction dependent and hence they are called unilateral. They are used for rectification. Rectification means conversion of bilateral current, bidirectional current into unidirectional current, regulation, generation, amplification, etc. Diodes used for rectification and such type of purposes, they are called ordinary diodes, whereas diodes used for generation, amplification, such diodes, they are called special diodes. Several types are there like ordinary, Zener, LED, photo, tunnel, varactor diodes, etc. This is a general small introduction to diodes, PN junction diodes. Now transistors. These are three-terminal devices, nonlinear devices. Sometimes they can have a fourth terminal too. We come across MOSFETs with the four terminals. These are used for amplification, generation, matching, etc. Several types are there like BJT, JFET, MOSFET. Notice diodes are mostly passive. They can be active too when they are used for generation of signal, when they are used in the design of amplifiers, then the diode is active. But mostly it is passive. Passive kind of application is rectification. Now transistors are mostly active. When they are used for acting as passive semiconductor slabs, then only we can say that they are passive. Most of the times they are active. Semiconductor crystals are used to fabricate diodes and transistors. Here is given a classification of solids. Solids can be divided into different categories. Here two classifications are given. One classification is based on electrical conductivity, another classification is based on atomic arrangement. The classification based on electrical conductivity, it divides solids into conductors, insulators, semiconductors. Conductors are materials having huge amount of electrical conductivity. Insulators are materials having no conductivity. They don't allow current to flow through them. Whereas the semiconductors are materials whose conductivity is in between conductors and insulators. Classification based on atomic arrangement is into crystalline, amorphous, polycrystalline. We discuss about these classifications further right now. Here is shown different atomic arrangements in solids. In certain solids which are called crystalline, notice the arrangement is regular. Atoms are in rows, in columns, in a regular, repetitive manner. Now come to polycrystalline. In polycrystalline, there exists a repetition. There also exists certain amount of randomness. In C, you can notice there are four atoms. These are repeating. These are repeating. These are repeating. These are repeating. So certain repetition is there as well. You can notice there is a certain randomness, certain amount of irregularity. This type of structure is called polycrystalline structure. Crystalline means complete regularity. Polycrystalline means partial regularity. Amorphous means no regularity. You can see here the atoms in the solid are located in a random fashion, no regularity. So on one end crystalline, on the other end it is amorphous, in between polycrystalline. Here is shown energy band diagrams of materials. In A, insulator band diagram is shown. In C, Conductor band diagram is shown. In B, semiconductor diagram is shown. Certain general points regarding energy band diagram. There exist two bands, one at the bottom, another at the top. Top one is called conduction band. Bottom one is called valency band. Valency band denotes the energies of electrons which are bound to the nuclei of the atoms or which are in covalent bonds, and hence they are not free. So valency band represents energies of electrons which are not free. Conduction band also represents energies of electrons, but these energies pertain to free electrons. They are free to move. Only free electrons can contribute to the flow of electricity. So conduction band electrons only contribute to conductivity, electrical conductivity. One can notice valency band at the bottom in all the three types of materials, conduction band at the top of the band diagram. When we come to A, which represents energy band diagram of the insulator, we can see there is a gap of 6 electron volts between conduction band and valency band. In case of semiconductors, this gap is hardly 1 electron volt. In case of C, there is no gap between VB and CB. On the other hand, these two bands are overlapping. In the band diagrams, EC represents minimum energy level of conduction band electron, EC. EV represents maximum energy level of valency band electron. EC minus EV gives band gap energy. Electrons are forbidden to have energies represented by forbidden band gap energies. In case of insulators, distance between EC and EV is large. In case of semiconductors, it is small, 1 electron volt. In case of conductors, no gap. So what are the implications of these observations? To increase conductivity, what is required to be done is carrier concentration or electron concentration has to be increased. How it can be increased? By pushing valency band electrons into conduction band. It is possible to increase free electron concentration, thereby increasing conductivity. In case of insulators, as the gap between valency band and conduction band is huge, it is almost impossible to push the electron from valency band to conduction band. Hence, insulators cannot be having any free electrons or electrical conductivity. In case of semiconductors, gap is small. So, energy necessary to push electron from valency band to conduction band, it is not that much great, and hence that energy can be given to valency band electron, pushing it into conduction band, thereby raising the conductivity. In case of conductors, there is no gap. Valency band electron can be in conduction band electron can be in valency band. They are overlapping. The distinction between bound and free electron is lost in case of conductors. So one can say all electrons are free. When I say all, I don't mean inner orbital electrons or electrons which are very much near to the nuclei. I mean outer orbital electrons. This discussion explains why insulators conductivity is nil, conductors conductivity is huge, semiconductors conductivity is in between. A few points regarding energy band theory. The electrical behavior of semiconductors can be understood easily with the help of energy band theory, energy band diagrams. It is associated with various energy bands, levels, which are described briefly here. The bottommost energy band is valency band and the topmost band is conduction band. These two bands are separated by a gap. It is called forbidden energy band gap. Forbidden. Electrons cannot have the energies that fall in the forbidden energy band gap. That's why it is named as forbidden. Energy level EV indicates the highest energy possessed by any bound or valency electron. Energy level EC denotes the lowest energy possessed by any free or conduction electron. Notice valence electron, bound electron, they are synonyms. Free electron, conduction electron, they refer to the same thing. The energies associated with the atomic electrons are very small, measured in electron volts. This is an important point one has to keep in mind. We use electron volts to measure energies in energy band theory, not joules. 1 electron volt is 1.6 into 10 power minus 19 joules. Electron volt is very small when compared to joule. Here, certain points are given regarding notation. EV, it represents maximum energy of valence electron. EC, minimum energy of conduction band electron. ED, energy level due to donor impurities. EA, energy level due to acceptor impurities. We come to EDEA again after completing this list. EG, band gap energy. EF, Fermi energy. ND, donor impurity concentration. NA, acceptor impurity concentration. NC, effective density of states at conduction band edge EC. NV, effective density of states at valency band edge. Now EV, EC, both are already introduced. Their meanings are also given. Now ED, EA. What is ED? To increase the conductivity of a semiconductor material, impurities are added. Two types of impurities are there: donor type impurities, acceptor type impurities. In case of silicon or germanium, pentavalent atoms, they act as donor type impurities. Trivalent atoms act as acceptor type impurities. When impurities are added, what happens is this particular level, energy level EC, it gets lowered. It gets lowered to a value ED. This is the case when donor type impurities are added. What does it mean? What is the implication of this lowering of EC to ED, to a lower level ED? Implication is the gap, forbidden band gap, now is small. Because of this smallness, reduction in the band gap, what happens is an electron which is in the valency band, now it has more probability, more possibility to jump into conduction band. So there is more chance for conductivity to be increased. Similarly, addition of acceptor impurities raises the energy level EV. It rises to a level which is indicated by EA. Notice rise of EV to EA. In this case also there is a reduction in the forbidden band gap. Reduction in the forbidden band gap means more possibility, more probability for valence band electron to move into conduction band electron, thereby rising the conductivity. So ED, EA, EG. EG means band gap energy. EF, Fermi energy. What is Fermi energy? Inside semiconductor, inside metals, other materials too, that exist electrons. Energy of several electrons, different electrons, it is not same. It means different electrons will be having different energies. Average energy of the electrons, it is given a name Fermi energy. It has certain special significance in energy band theory. Next, ND. It refers to donor impurity concentration. As already mentioned, to increase the conductivity of semiconductor slab, impurities are added. Two types of impurities are there: donor type impurities, acceptor type impurities. The concentration of donor type impurity, it is indicated by ND. The concentration of acceptor type impurity, it is called Na. It is denoted by Na. D stands for donor, A stands for acceptor. Capital N means concentration. Nc, Nv, these are density of states. Nc, C refers to conduction band edge, density of states. V refers to, Nv refers to valency band edge, density of states. A few points regarding band gap. The band gap energy, Eg, represents the energy range which is forbidden for any electron in the system to have. It is also equal to the minimum energy required for a valence electron to jump into conduction band, becoming a free electron. Also note, when conduction band electron moves into valence band, energy at least equal to band gap energy is released. Using Planck's law, the wavelength of the radiation can be found related to band gap energy through this relation. Lambda wavelength in micrometers is equal to 1.24 Eg electron volts. What is this? Consider energy band diagram of semiconductor. At the bottom it is valency band, at the top it is conduction band. Let us suppose there is an electron in the valency band. For this electron to jump into conduction band, it requires a certain energy. This energy has to be supplied to the electron. Then only it can jump from valency band to conduction band. When it jumps, it becomes free. In valency band, it is not free. In conduction band, it is free. The point is, for an electron to move from valency band to conduction band, certain amount of energy is required. Somebody has to give that energy to the electron. Now, consider the inverse process. A free electron, an electron which is in the conduction band, falling into valency band. Conduction band means the electron is having high energy, more energy when compared to its energy when it was in valency band. Now, if a conduction band falls into valency band, the energy difference, energy of the electron when it is in the conduction band, energy of the electron when it is in the valency band. That difference, it comes out. It comes out in the form of a radiation. Radiation is associated with certain frequency. The energy of the radiation and the frequency of the radiation, these two are related by a law. The name of this law is Planck's law, E equal to hf. This law can be manipulated, modified, so that a law connecting energy, band gap energy, and wavelength of the radiation, these two are visible prominently. The point is, important point, which we have to keep in mind here in the discussion is minimum energy that is required for the electron to move from valency band to conduction band, or energy that is released when conduction band electron moves to valency band. How much is this energy? He says this energy is equal to gap energy, Eg, band gap. The forbidden energy gap, Eg, it is equal to, of course, Ec minus Ev. It is a temperature dependent parameter for any semiconductor material having maximum at absolute zero temperature. It decreases with increase in temperature, which can be described mathematically as Eg equal to Eg naught minus B beta T. T is temperature. Eg naught means band gap at absolute 0 degree temperature. Here Eg naught is forbidden energy gap at 0 degree Kelvin. Beta is a constant with a value equal to 3.6 into 10 power minus 14 for silicon and 2.23 into 10 power minus 4 for germanium. For silicon, the gap energy is 1.21 electron volts at 0 degree Kelvin, 1.1 electron volt at 300 degree Kelvin, that is room temperature. For germanium, it is 0.785 electron volt at 0 degree Kelvin and 0.72 electron volt at 300 degree Kelvin. Notice in both the cases, it is decreasing with temperature. At 0, it is 1.21. At 300 degrees, it is 1.1. Decrease from 1.21 to 1.1. In case of germanium, the decrease is from 0.785 to 0.72. Now a brief comparison is given between insulators, conductors, and semiconductors. Insulator. Number of conduction band electrons is very small, 10 per cm cube, and hence negligible conductivity and negligible current exists. Energy gap is large, hence very difficult for electrons to jump to conduction band due to thermal excitation. This is the case with insulator. Now come to conductor. Number of Cb electrons is very large, 10 power 22 per cm cube, and hence more conductivity, more current. Energy gap very small, negligible, and hence electrons easily jump into conduction band due to thermal excitation. In fact, there is no gap. These bands, conduction band and valency band, they overlap each other. So an electron, it is bound simultaneously, it is also free. Next point, conduction is due to electrons only. Come to semiconductor. Number of Cb electrons is in between insulators and conductors. Conductivity and current is very little. Energy gap is moderate, and hence due to excitation, a few electrons can jump to conduction band, leaving holes behind. Here conduction is due to both electrons and holes. Now we come to the end of the session. Before closing down, let us recollect important aspects that are touched upon in the present session. The focus is mainly on energy band diagrams of materials like insulators, semiconductors, and conductors. The differences between them in terms of energy band diagrams. Different energy levels, different energy bands associated with energy band diagrams are introduced. A comparison of semiconductors with insulators and metals or conductors is given. Hope this session is useful to you. We meet again in another session with a new topic soon.